In section 2.3, we want to briefly look at organic chemistry. So we're going to define organic chemistry, discuss the importance of carbon. We're going to describe how atomic structure affects chemical bonding. We're going to compare and contrast covalent and ionic bonds. And then the end of the section, briefly look at acids and bases on the pH scale. So first off, organic chemistry. So why in the world are we talking about organic chemistry in biology? Well, organic chemistry, we know that chemistry is very important in biological systems. And so when we talk about the term organic just basically means that it's going to include both carbon and hydrogen. So carbon is a very, very important atom, or a very, very important element when we talk about living things. What's so important about carbon is that carbon interacts with other elements to produce very complex molecules that are making up living things. So we have these things called hydrocarbons, where you have carbon binding with multiple hydrogens or multiple other atoms, and you can form all these different molecules that make up living things. So again, carbon, because of the number of electrons it has, it's able to form up to 4 different bonds at one time. And so because of that, like I said, it becomes kind of like a chemical tinker toy or connector that can join all these different elements to build these pretty complex molecules that living things need. So carbon is a very, very diverse atom that is very important to biology. Now, one of the important things to note, again, and we've mentioned this in the last section, is chemical bonds. We know that bonds are happening between atoms. And so the question is, well, what determines who bonds with who and how they bond? Well, first off, you need to understand that atoms bond only to gain stability. See, with atoms, there are a couple of magic numbers that you would want to know. So remember when we talked about at the beginning of chapter 2 that for any atom, in the very center of the atom you would have protons and neutrons, and then around in these outer shells or orbitals or clouds, if you will call them, you'd find electrons. And so for every atom, the very first shell, the magic number is 2. And so what that means is that this first shell is considered to be complete when it has 2 electrons. Then if there are any remaining electrons for that atom, they fill in the other shells. And so for every other shell, second shell, third shell, fourth shell, all the way out, their magic number is 8. So they're said to be complete at 8. Now, why do these numbers matter? Well, if an atom has the magic numbers, so if it only has one shell and that magic number has 2, then we say that it's stable. Or if it has multiple shells and all of them are complete with those magic numbers, again, we say that the atom is stable. It doesn't need any extra electrons. It doesn't need to get rid of them. If it has the magic numbers, it's stable. However, if an atom, does not have the magic number, then it's going to try to bind with other atoms in order to gain those magic numbers. So it's very important to understand that bonding is very dependent upon the number of atoms or the number of electrons that an atom has. So for example, we use the term valence shell. Valence shell is what we call the outermost shell. Like we said, those outermost shells, they have magic numbers. So if the outermost shell is full, having those magic numbers, again, we call it stable. It doesn't need anybody else. It will not form bonds. However, if it's not full, it will look to form bonds in order to become stable, and so we call those atoms reactive. So if you look at this example, sodium. So sodium has multiple shells, and you'll notice the first shell is complete with 2, second shell is complete with 8, but the third shell only has 1 atom. Now again, remember, in shells 2 and 3, their magic number is 8. So if they only have 1 in the outermost shell, but they need 8, we would consider this to be a reactive atom. It's going to look to bind with something else in order to gain the magic number. Look at chlorine. Chlorine by itself has 2 in the first shell, which makes it complete, 8 in the second shell, which makes it complete. But when you look in the outermost shell, it only has 7. Now again, remember the magic number here is 8. So if sodium only has 1 in its outermost shell, chlorine only has 7 in the outermost shell, both of these atoms are reactive because they're looking to get those magic numbers. So what actually happens here is sodium gets rid of that 1. When it gets rid of that 1, it no longer needs that outer shell, and so now its outer shell has the magic number of 8. So by getting rid of the 1, sodium becomes stable. At the same time, by gaining that 1, chlorine that had 7 now has 8 in its outermost shell, and it also becomes stable. So it's all about the number of electrons that they have in their outermost shell. If they have the full number of electrons, they're stable. If not, they're going to look to bind with something. So briefly, let's look at the two major types of chemical bonds. To begin with, we're going to talk about covalent bonds. In covalent bonds, these are atoms with 4 or 5 electrons in the outer shell. They tend to share electrons to complete their valence shell. So the key word with covalent is the word share. We see this happen. They can share one pair of electrons. They can share multiple pairs of electrons. And so we see this happen, like for example, atmospheric oxygen shares, or that you look at methane here, or ethylene. These are where atoms are bonding together by sharing electrons. But covalent is not the only type. The other type of chemical bond is an ionic bond. In ionic bond, there's no sharing. Instead, the key word is to transfer. So ionic bond is like the example that we just looked at with sodium and chlorine. So atoms with 1, 2, or 3 electrons in their outermost shell, they're going to tend to give them away, like sodium did. Atoms with 6 or 7, they're going to look to gain electrons, like chlorine did. And so when electrons are transferred from one atom to the other, it holds them together and forms an ionic bond. And so since atoms are either losing electrons or gaining electrons, they then become electrically charged atoms, which remember we call ions. So covalent bonds, they share electrons. Ionic bonds, they transfer. And again, that was the example of sodium and chlorine. And then the last topic that we're going to look at in this section is the pH scale. Now, you've heard of this before, but the pH scale, you'll notice, goes from 0 to 14. And on the pH scale, this is where we register if a solution is an acid, a base, or neutral. If it's an acid, it has more hydrogen and less hydroxide. Because of that, it has a pH below 7. A base is going to be the opposite. It has more hydroxide, less hydrogen, and so on the pH scale it registers greater than 7. So acids that would be below 7 include things like, I mentioned, coffee, soda, orange juice, battery acid, in your stomach, hydrochloric acid. Things that register as basic, a lot of your household cleaners, baking soda, ammonia, drain cleaner, Clorox, those would fall under the basic category. And then substances that have equal hydrogen and hydroxide, they register at a 7 on the pH scale, which would be considered neutral. Very few things are neutral. Pure water, not what comes out of the faucet, but pure water would be considered neutral. So very quickly, in review of this part of Chapter 2, in the first section, second section, and the third section, these would be the learning objectives that we covered.